Guys, we kick off then. I trust you're all set up and you've got something to look at. I'll show the slides on here. So just to let you know, I've merged the slide content into the notebook. Okay, so you'll see the exercises in here as well as the slide content. All right, so here we are. First session, we're just warming up, we're just recapping. So let's get through this. All right, so here we go, basic types. So who can tell me what type we see, what type of data do we have represented here? It's a string, and how can we tell it's a string?
It's a word.
It's a word, yeah, correct. And another giveaway about a special symbol that we see at either end of the literal value. Yes, that's it. It's the quotations, isn't it? It's the speech marks. Double quotes. Can I use single quotes in Python?
Yeah.
Ooh, a little bit of divide of opinion. Should we try it? Should we see? Let's use single quotes here. Let's replace those. And let's give it a run. Yeah, and we can also print it out too. Let's just check that. Yes. Oh, well, in Python we can. So other languages, you're right, it would be treated as a different type of data. Does anyone know what the single quotes is in something like C or Java or C++? Otherwise known as a character. So a single character is a single quote, and then double quotes is a string. Okay, but in Python, interchangeable. We can have single quotes or double quotes. Okay, so there we go. Just worth remembering that. Another handy function in your toolkit is the type function. So again, if you're not sure, you can call the type function, pass in that variable, and then you get the type str string in Python. Okay, it's fairly simple, wasn't it? Let's have a look at the next one. What data type do we see here? Boolean, very good, yes. And the other value would be other than true. If it's not true, it would be, yes, correct. So Python, just remember it's capital T for true, capital F for false. All right, again, C languages, Java, it's lowercase, but in Python, it's uppercase, okay? So just remember that. Age, here is a what type? Integer, yes, because it's a whole number, correct. Built as int in Python. Again, we can confirm that if we just type, use the type function. There we go, int, nice and easy. And then finally here, this is known as a float, yeah. So in other languages, you might see double. You might have double and float in some languages, but here in Python, it's just built as a floating point number. You probably would have done this when you had a look at architectures, look at all the floating points and the number of bits that you have. So just remember in Python, it's a float. All right, so these are our elementary types. They're actually built different to primitive types, it's worth saying. So in other languages, you would have lowercase type names for these, like int lowercase, float lowercase, char would be lowercase. They're primitive types. But in Python, are they built as primitive types or are they built as something else? Ooh. Do we think they're primitive types in Python? Yes or no? Can we remember? Oh, silence. All right, well, let me help you out then. All right, so if I tell you what, if I put print in front of this, we get a little bit more information. Ooh, what's that? Class. And do we remember what we create of classes? What do we instantiate from classes? Anyone? What do we instantiate? What do we create from classes? There's a second word. Yeah, okay, so an instance of a class, which is otherwise known as it's a keyword I'm looking for. Classes and objects, that's it. We create an object of a class, yeah? So they're not built as primitive types in Python. The answer to my previous question, they're not built as primitive types because they're built as classes, which means they have stuff with them. They have attributes. They have methods. Okay. Let me see if I can demonstrate that to you. If we just look at the directory of one of these, guess what we see? We see a load of stuff, don't we? I can even show you the full list. We see we haven't actually got the parentheses here, but we've got these. Does anyone know what these are, actually? Let me ask you. We have 2 underscores here. Does anyone know what those are otherwise referred to? Oh, let me show you a famous one. So you'll probably, hopefully recognise this. Is it here? Yes, it is. Does anyone remember this? Init. Not street talk, but short for initialization. You'll see this in just a minute. We're going to get to it with classes, but this is the constructor. Okay, it's got 2 underscores, double underscore. It's a method. You don't see the parentheses, but it is a method that we'll be calling. What we do is we abbreviate double underscore to be dunder. So you take D of double and under of underscore to get dunder. They're known as dunder methods, all right? So we've got a whole host of these dunder methods. They're kind of behind the scenes methods. So when we will interface with inits directly, but usually, most of the time, we do interface with the non-dunder methods, and they will call the dunder methods behind the scenes if you're trying to perform additions or subtractions or whatever it is. The Python interpreter kind of manages the context for what they do, okay? Because if you add 2 numbers together, it's very different from concatenating 2 strings, isn't it? You have to overload the operator. So in something like C++, you'd probably do that manually. You'd specify what the overload is, but Python behind the scenes manages that for us, okay? So that's useful. So what my point is that built of classes, these types, and let's look at int as well, if we can show you that. There we go. We've got another list of things that we can refer to. Numerator, real, to bytes, from bytes. There's a whole host of different methods that we can call that are they're packaged in with a class, and when we create an object of that, we can call these methods. Okay, get the size of, convert to a string, truncate, apply the XOR gate to it, bit length, conjugate, a denominator, from bytes, all these things that we can use with those types, okay? So that's quite useful to know. Indeed, dir, directory, is what it stands for. It's quite a useful function. Bless you. I've given the type function, I've given you dir function. These are going to be useful things for your toolkit, so store them away. We'll be referring back to them, all right? So my main point is that these are classes, they're not primitive types, okay? So primitive types, you wouldn't have any attributes or methods with them, but classes, as we know, we do, all right? So useful thing to point out, as we see here. Okay, yeah, so just in a bit more code type, printing the types. We've got a integer and we've got a string, okay? In Python, can I change the type of data that I store at a variable? So you see here we've got an integer. I've already done it, sorry. That should be age. So if that was age, let's do that there and print the type for you. Age, okay, so age starts out as an integer, and name is a string, but could I store a string at age, and vice versa? Could I store an integer at name in Python? Is that legal? You just saw it. Yes, it is. You just saw it. So let me show you it again. All right. So at age, if I now overwrite that with my name and print it out, guess what? We see that the type of age is now a string, and I can overwrite what was previously there. So it's previously an integer, and overwrote it with a string. So in other languages, you're going to get told off for that. It's going to say, no, you can't do this. You have to either create a brand new variable with a type, because remember in C and Java, you specify the type, don't you? But in Python, we don't specify the type up front. And we can therefore point to a different type of data. So really what we're getting at here is we're using pointers to objects behind the scenes. C++, you do this manually, have a pointer variable which points to a memory storage space. But here in Python, we don't have to do any of that. We can literally just change the type of data and it manages it for us. It's pretty cool. So that shows us we can overwrite other types of data. We can change them. They're not statically bound. So that's the key word here. If you declare the type up front, you're binding that memory location to the size that's allocated. So if you're dealing with like a 64-bit integer or a 32-bit integer, you can allocate enough memory to store data of that size. Whereas a string is a different size, a char is a different size, a byte is a different size. But here in Python, they're just pointers to objects. So we can change where it points to. You know, we can pick one bit of data, point to it, and then pick another bit of data, point to that. All right. Happy with that, guys? Any questions on that? Does that make sense? Okay, because we're going to see quite a bit of that. Pointers, referencing, referring to data. Okay, so that's one key thing in Python we need to be aware of. All right, let's move on. All right, so conditionals. Hopefully stuff that's fairly elementary. We've used if statements before, else statements. What could I put in between an if and an else there if I had more than two options? Elif, correct. Very good, very good. What are the advantages of using elif over just multiple ifs? Anyone remember? Tavik again? Yes, correct. There are more conditions, correct. But could I just put if statements there if I had more than? Is there an advantage to using elif over if? Because I could just put a load of if statements. And potentially, if I've coded it to be safe, or Marcel? Yes, maybe. I suppose elif is a little bit shorter than if. I don't think it's necessarily less code because I'm still going to have some sort of response to it, a return statement or a print statement or some action taken. So maybe not less code. It's more about the exclusivity of elif. Because remember else? All right, well, let's actually focus on else then.
Or is it that it's more specific?
It's more specific. Yeah, we're getting warmer. Good. So what would be the condition for else to run? Why would else run in this particular context?
All conditions are wrong.
Conditions are wrong, correct. Yes, that's right. Yeah, so if, that has to not be true, false in other words, for else to run, doesn't it? It can only be true or false. Can't be true and false, unless you're in quantum computing or something like that. But assuming we're in our 3D world, where true and false are mutually exclusive, yeah, it's only ever true or false. So if it's not true, it's otherwise false. So if we put else ifs in there, elif would mean that the above is false, wouldn't it? Whereas if we had a load of if statements, potentially, they could all be true if they weren't coded very well. If we hadn't thought through the logic, multiple if statements could be true. Okay, so that's one safeguard we're using elif. If we want to make sure there's only one return, only one outcome, only, they're mutually exclusive, it can only be one rather than multiple, elif would prevent multiple if statements triggering. Okay, so that's the basic gist behind it. All right. In this case, it wouldn't apply because it's only ever true or false. But if I had a series of statements, we always use the grey boundaries, don't we? So, if you've got between 0 and 40, 40 to 49, 50 to 59, 60 to 69, 70 plus, we'd return a grade. So that's where we have multiple statements in a function. And that's probably a good case to use elif rather than if, just in case, one of the conditions was less than 50, if you got the score of 45, well, that would tick the box of being less than 50, but it may also trigger some others as well if you've got some other if statements in there, or pick anything in the scale, and it might fulfill multiple if statements. Okay, so summary of the point, yes, elif is exclusive, like we see here. All right, so I trust we're okay with that. In this case, it doesn't apply because it's only dealing with true and false, so we only have two options. But just be aware for more conditions, it's best to use elif, of course. Unless you want multiple conditions to be true, that is. There may be situations where you want multiple outputs, so just think that through. All right, so here we're just testing it. If I pass 10, this is all about is positive, so if num is greater or equal to 0, return true. And we see that, so that's good. For 10, it's a positive integer, whereas if we return, if we pass in -1, it gives us false. All right, so I trust we're okay on just functions. You know, def, remember, is define in Python. You need a colon. Indentation's essential, by the way, for Python, in case you didn't know that. I wouldn't be able to write this. It's going to tell me off. It expects it to be indented. I think vice versa for here too. So thankfully it will tell you if you're missing indentation. Just be aware if you're copying code from somewhere, there might be slightly different formatting. In case you've done a load of spaces or something. You know, just be aware of that. Sometimes the spacing is different. I tend to use tabs if I can, just to protect it. So just be aware of that. But yes, you definitely need indentation. And VSE, you can see the lines, so that's helpful. All right, so just remember that. No parentheses needed for the if statement. Again, if you're in other languages, you usually do have them, but in Python, not necessary. And then else, of course, colons. So just remember those. All right, so yeah, hopefully fairly basic stuff. Hopefully we're okay with that. Okay, let's talk about OO. So we've already established, remind me, what do we create from classes? We create, objects. Thank you, objects, yes. So how do we define a class? Does anyone want to offer a definition of a class? What do we have in them? What types of things do we define in the class? What is a class? Or class? A group. Okay, expand on that, Adele. As a group of?
Like integers, for example, is like a group of numbers.
Okay, yeah, we could, and you're right, we could create multiple integer objects of the int class, yes, correct, we can do that. Okay, so what, let's push that further, what would that then tell us about what's in the class? If we're going to create multiple instances, multiple objects of a class, what types of things do we want to put in the class that our objects will have? Thank you. Attributes, yes, so variables, right? Yeah, so we all have attributes, don't we? Use the student example if you remember from last year. So you're all students, you will have names, you will have IDs, you will get marks. So they're just attributes of you, aren't they? You know, we can list loads, can't we? Hair colour, eye colour, you know, height, weight, all the stuff, you know. Just attributes, characteristics essentially that have values, okay? So that we can define those as variables in our Python classes, yes. Give them values. Even more specifically, we can create multiple objects which have unique values. You all have unique names, so we can have an object for each one of you. You all have different names, different ID numbers, different hair colour, eye colour, you know. So that's good. Okay, so we've got attributes, and then what else do we have typically in a class? Thank you. Yes, methods, so behaviour, psychological. The psychological terms of kind of attributes of something, someone, and behaviour of some entity. Okay, so we call them methods. Some people might call them functions. Technically, I think OO terminology likes to side with methods. It could be a function if it's outside, or termed a function if it's outside of a class, like we see here. This isn't part of a class. It doesn't sit in a class, so we could call it a function, technically, but inside of a class, we'd advise to call it a method because it belongs to an entity. Okay, procedures as well. There's loads of terms. It depends what book you read. It depends what sphere you're from. Languages sometimes have their own terms and naming conventions and all that. But yes, methods and attributes. Those are the two things we generally see in a class, don't we? We've already established that int, str, float and ball are classes. So here's a classic example of a car. So a car is the entity, that's the class. And guess what? You get many different types of car, don't you? So we all drive, probably all of us would drive a different car, unless we've got any overlap. But we're probably all likely to have a different type of car. That's going to have attributes of, what's the fuel gauge on it? How many litres does it store? What's the max speed it could do? How many years old is it? How much mileage has it done, etc.? All the kind of characteristics of an individual car. We could define those in a class so that our car objects can add values for those attributes, okay? And then, of course, the cars have behaviour, don't they? We go to the fuel pump or the electric refill station if you have an electric car. So that's the refuel function. We also have get fuel, get speed, and others as well. 2 get speeds, I think. Drive. Yeah, types of behaviour, types of functionality, types of things they do. Okay, so those are the two things we tend to see defined in the class, and they're defined up front, it's worth saying. So when you define the class, you haven't yet created the objects of them. So it's really just a skeleton structure, which I think is kind of what's being indicated here with the kind of dashed line. It's like an outline of a car. It's not a physical car. It's not yet been instantiated, so it's a kind of a template, a blueprint, let's say. That's probably a better definition of it, a blueprint. It's kind of on paper. It's the design of a car, what a car should have, but we have to then instantiate it, bring it to life as an object, and then give it values, okay? So here we go. We've got specific cars now. An Audi, a BMW, okay? And the models and the different years that they're produced, different generations of cars all have their own different objects, okay? From that blueprint, from that template, we can then create physical instantiations. We can bring it to life, all right? So an object. So there we go. Good to be reminded of that. That's our 00101, essentially. And there you go. That's UML form, if you wanted to have a look at this. UML diagram. A little bit old school these days, UML, but still useful to know about it. If you're designing something from scratch, it's good documentation. Good to see the kind of the blueprint of what it looks like. So we've got the class there, we've got the attributes, the methods. You can tell it's a method quite easily if it's got parentheses. Okay, fairly straightforward. Other languages, you define the data type. So if it's statically bound, we've got here, haven't we? Name is of type string, ID is type integer, balance type double. Okay, so just showing you what you already know. Oh, and objects as well, yes. So different objects of that class. All right, so let's have a look at it in Python. How do we actually write them in Python? Well, nice and easy. Class, okay, keyword class, quite simple. Okay, so keyword class, I believe the convention is uppercase for Python. Definitely is in other languages. But for entity names, usually they're uppercase. All right, so uppercase S for student, class name. And then, of course, we define our methods in here, not functions. They look like functions, but they would count as methods because they're defined in a class, okay? In this simple one, just printing name, and it's nick, okay, in this case. So do you remember what self does? Does anyone remember what self refers to? Or what the importance is of self in OO? Anyone? Anyone want to offer a definition for self? Silence. Okay, all right. How can I best illustrate this? Okay, Ali, if you say myself, go on. Myself, yeah. Tavikian, say myself. So who is who? Who's self? So when I say myself, I'm Nick. And when Ali says myself, it's Ali. Tavikian. If we are 3 different objects, self refers to me, the current object. It's referring to me, isn't it? So it depends who's saying self, doesn't it? So what I'm trying to illustrate is that self is a placeholder. It's not a specific object, because the idea is to reuse it for any object, isn't it? So I can't hard code it. I can't put like the object for Ali, the object for Tavikian, Tyler, Harry, whoever in here, because it's only going to refer to them. So, but if I put self in there, it's going to refer to the current object that's operating on, on the class, who is ever calling the functions for that object. Okay, so it's an abstract term. In other languages, it's referred to as this object. In Python, it's self. It's me, whoever is calling at that time. Okay, so it's a bit abstract, something to get your head around, but that's going to become important because it's going to show up in all the classes that we write. Indeed, all the functions in those classes, otherwise known as methods. Okay, and here we go. We're actually creating an object of that class. So we spoke about it. How do we do it? Okay, well, it's here. So we have to call. Oh, let me ask you. We see the parentheses here, so that usually tells us something about this thing here. It's a thank you. You got it. It's a method. It's a method with the same name as the class. Thank you. So a method with the same name as the class is a constructor. Yeah, it constructs the object, instantiates the objects, brings it to life. All the things we just spoke about. All right. So we call the constructor. That returns a memory reference. Store an object, obj, okay, and then we can call a function on that object. But whose object? Well, in this case, it's obj. So the memory reference for obj will become self, because it's obj calling that method. Equivalent of Ali calling the method, or Tavikian calling the method, or me calling the method, or Harry, Malika, whoever is calling the method at that time, it will be their name, it will be their details, it will be their attributes and the methods for which operate on those attributes. Okay, so the class allows us to define structure that we can reuse for any of the objects that we create from it. Okay, I hope this is all kind of fitting together in your brain and you're starting to see how all these components fit together. All right, so that's the theory and the practical with it. Just to give you something on the object address, yes, the memory address, I told you it was a reference. So what do we see here? We see hexadecimal. All right, we've got a mixture of letters and numbers. Okay, so base 16, or maybe a bit more because we've got X, but 0 to 9, and then A, B, C, D, E, F for hexadecimal address here. So base 16 rather than base 8 or base 2. All right, and it's an object. It's of student type. It's a student object because it's an object of student class. All right. So if you were to print obj, you'd get the memory address where it's being held. Okay, it has to be of enough memory so it can store all the individual values for attributes and have references to all the functions or the methods, of that class structure. Okay, so every object you create has its own address. All right, let's create multiple objects. Let's show you that. All right, so here we go. We're going to run this. Let's have, I need to define this probably. Let's run class, let's make sure that runs okay. And let's run this. Oh, hello there, welcome. So here we go, we're calling the constructor twice. We're returning two references. We're storing the first one in Nick and another one in Sam, because we've got two objects, we're calling the constructor twice. Let's print them both out, and you can see, subtly, they are different. They're very similar up until a point, but they're very slightly different there. Okay, so different addresses, different locations in memory, two objects. All right, so that's the purpose. We can create a class structure that can be reused, that can be instantiated, not just once, not twice, multiple times. Okay, as Ali said, a group of objects, a group of integers. Sorry, Adele said that. So that's the purpose, that's what we're trying to do. But in this case, I've got a slight problem because in my print name, I've got a static print here. It's only printing hi Nick, so it'll only say hi Nick on any objects. So this is where self is going to kick in, because therefore we can use self to refer to a attribute of self. So if we have a look at this, we're going to set the name for self's objects. Remember, self could be anyone that's calling it. It could be Ali, it could be Adele, Harry, Malika, Tyler, Tavikian, Amara. Welcome. So it depends who self is. if it's me, if I'm self, if I'm the object calling this, well, it's going to set my name. Okay? So name is an attribute, we established that. And we're going to set it via self. All right? So the advantage of this is that we can set names for each of our objects. Okay? So if I pass Nick in to this setName method, it's a method because it resides in the class, there it is, and I refer to Nick.name, well, it's Nick object's name, which is what I set it to be, Nick. Okay? Let's see that in another scenario. Let's create two objects, so one for Nick, one for Sam. And there we go. We've got around that problem because we are setting names for each object. We're setting values for those attributes. We're making use of what we defined in the class so that we can set the values for them. Okay? And if we take that a step further, let's actually put all of that logic in the constructor. Ooh, we returned back to something I mentioned earlier. Does anyone remember what we called this? Two underscores, otherwise known as a... Thank you, dunder method, yes, there it is, it's kicking in now. And this is going to be our constructor in Python. So we're going to define it ourselves. It's a dunder method, as mentioned there. It's called by the Python interpreter. You may have noticed, actually, by the way, we didn't write init here, did we? We actually wrote student here. Same name as the class, constructor, correct. But we didn't define anything for the constructor, did we? So where did the call go? It's a method, right? It should call a block of code. But where's the block of code? It's not there. There's no student method there, is there? So where did it call? Anyone? Let me tell you, it's the inits. It's the init methods. So guess what I said? It sits behind the scenes. If it's not defined explicitly, it's behind the scenes. The Python interpreter is going to call it to initialize the object. It's going to create some memory for us, and we can assign data to it. So what we're going to do here is we are going to overwrite it. We're going to specify some code for it. So this is why we have define init, dunder method, reference to self, reference to name. That's our just local name that we're passing in to set. I had an explicit method called setName before. Now we're going to put that logic in the constructor, a bit more appropriate because it's constructing the object, setting the initial values, initializing the values. So we're going to put it in there. Okay, and we're going to set the name of self. So remember who is self? Well, it depends who is calling this method. Self's name will become what we pass in, okay? And that's going to take place now in the constructor. So where am I going to have to pass a value now? Let me try and rephrase that. So if we previously passed the string, Nick, Sam, whoever, to set name, where am I going to write that data now to be able to get it to here? Anyone? Remember what we said about init? Init we call it's about track. Init is what type of method? Dunder method, thank you, yes. And did we say there's something special about this one? It initializes the object. So what initializes the object? Otherwise known as I think building sites. Constructor. Thank you. It is the constructor. When do we call the constructor? Constructor has the same name as the class. Yeah, so we call that when we create the object. Let me just quickly show you this. Here it is. Here's the constructor. Okay. Nothing's being passed in there, is it? Nothing's being passed in there. But could I now pass something in the code below? Because I previously had a setName function, didn't I? A setName function. But the whole purpose of me writing the initialization function was that it could take a name. Yeah. So we pass it to the constructor. All right, so that string, if that goes into the constructor, that's then going to route through to init. It's going to go into here and then be set there. Okay, it's all going to be done in the constructor there. Make sense? Are we seeing that? We're just joining all the things we were talking about together. All right, so you could have a set name function, by the way, it's not a problem. You may well do that, so it's perfectly reasonable, absolutely fine. But you might want to utilize some of the constructor functionality because it is the logical place to initialize values. You commonly do this. If you know the values up front, you can set them in the constructor. And you can change them later if you need to. So I might set an initial mark, pre-moderated mark for your assignment. Goes through a series of moderation. Maybe some are increased, maybe some are decreased. Hopefully not too much of that. Depends on how the moderation goes. Maybe I need to uplift you all. Maybe I've been too generous. Maybe I need to bring some of you down. We'll see, we will see. But we can set any value. We can change the values, okay? That's the reason why we have the self there. Okay, so put this all together and guess what we get? It seems pretty simple, but we're just trying to establish the routing of applying OO in Python. Just trying to recap all the stuff we did last year, just to kind of refresh your memories and bring you up to speed, okay? Because we're going to be using a lot of classes, writing our own, using a lot of objects, okay? So it's good that we get the foundations before we move on. All right, so there we go. We've passed it into the constructor. That returns an object, self. Remember that refers to self, yeah? And then by that named object, I can get to that particular value via the name attributes, which is here. Okay, so it will read as nick.name. What is that? Recall it, and then print it to screen. Okay, and then I think, yeah, we just expand that a bit more. We start putting the constructor together with print name. And guess what? That also has a reference to self because it resides in the class. We're going to need to know who it is, which object's name it is. If we're going to print it, who are we referring to? Well, it's the generic placeholder for self. So if Ali calls it, it's going to be Ali's name. If Malika calls it, it's going to be Malika's name. If Harry calls it, it's going to be Harry's name. Tyler, whoever, okay? Whoever calls it, it's going to refer to their specific attribute, the value which was assigned in what? The constructor. Okay? Let's move on. I think we're probably close to the, this is the last section, I think, inheritance, okay? Does anyone remember what we refer to by inheritance? Think of our social world, of course, inheritance. The passing down of resources, yeah, from one generation to the next, yeah. So what does that mean for our classes? Can classes inherit from each other? Well, the answer is yes, they can. The answer is yes. They can inherit from each other. We can encode that into our classes. Does anyone remember how we do that?
Parent, child,
Thank you. Yeah, that's the terminology. Yes, indeed, it is. Yes, so we might establish one class to be the parent, and then we might establish other classes to be the children who inherit from the parents. Okay, so the idea is to centralize the common attributes, the common methods. We said those were the parts of our class, didn't we? So, as normal, we would have those in the parent, and the children can draw them down. They can refer to them. Saves them duplicating it, doesn't it? If we've got lots of children who share a lot in common, rather than declare it, rather than having a name in every single one of the children, we could put the name in the parent and then reuse that code. And we're still trying to be efficient here. We're trying to reduce duplication. So that's one of the advantages of inheritance. Okay, the drawbacks as well, of course, but that's one of the advantages. What do we see here? We see a car and then a bus. A bus is a car, apparently. It depends how big your car is, how big the bus is, if it's a mini bus or something. So, and then a taxi. Well, I think a taxi is more logical. Not sure about the bus. Maybe we could debate on that. Maybe vehicle would be a better generic term. But I guess that's the point here, isn't it? We want generic terms, generic classes to be the parent, have all the common attributes, common methods, names. What else do these vehicles share in common? Well, we've got mileage, we've got fuel gauges, fuel tanks, max speeds, okay? We could put all those as attributes. You know, move forward, refuel, all the typical behaviours and methods in there in a vehicle class. And then if we move car down, we can have cars, buses, taxis, trains, coaches, any other motorbikes, whatever, any other type of vehicle, bicycle, if you want, that inherits from our generic vehicle class. Okay, it saves us having to define the same attributes in all the children. Okay, so that's one of the advantages of inheritance, to let you know that. And again, we see UML, so we see the arrow pointing to the parents. Okay, so that's just classic UML. We point to the parent, means the children are inheriting from the parents. Does anyone know any other keywords, any other terms that we use for those two distinctions? Parent and child. Does anyone know what other types of terminology we'd use for that? Are you familiar with, oh yeah, Oscar.
Superclass and subclass.
Perfect, thank you. Super and sub, yes, absolutely. And that super is going to become important, so make a mental note of that, because we'll see that in Python, okay? And there's also other ones, there's base and derived as well, yeah. So those are, depending on which book you read and what type of world, what type of background you come from. I quite like parent and child, probably because it reflects our social world. You know, easy to refer to because it's visible. But yeah, more engineering terms, more kind of mathematical terms like base and derived, and super and sub. Okay, yeah, and super is going to be important. Let's talk about super because, actually, sorry, before we get to super, let me just show you how to do inheritance, and then we'll talk about super. So in Python, it's this, okay? So we've got two classes here, parent and child, appropriately named as parent and child, okay? And to inherit from the parents, we would have to put that class name in the parentheses. Okay, that's how we do it in Python. Different in other languages, as we know. It extends in Java, colon in C and C++, base in C#, so lots of different terms. But in Python, it's parentheses, okay? And that means we can get access to the parents from the child. So let's have a go at this. Here we go, here's a good little test. If we create an object of the child, and we call child obj print, which one of the two print methods do you think we're going to call? Are we going to call hi from the child class, or are we going to call hi from the parent class? Both called print. So which one do we call? Anyone want to... which one though? Which print? Are we calling the child's print or the parent's print, Ali? Which one? It's a child object, remember? So it's an object of this class. But remember, we've got inheritance, so we get access to the parents. So which print do we call?
Parent.
You think it's the parent? Oh, okay. Who thinks parents? Hands up. Go on, be brave. Okay, Malika, yeah. Okay, okay, Ali, yeah. Anyone else for parents? No? All right. Oh, Oscar. Oh, Oscar. All right, parents, okay. And how about child? Do you think we call the child's print? Hands up for that. No votes for the child. All right, so we most of us, Marcel's voting for child. All right, okay. So more voted for parents than for child. Should we put it to the test? Should we have a go at this? All right, well, let's run our code then. Let's give it a run. We need to first compile. Let's first get these ready. Load them into cache, and let's run it. Okay. Hi from the child class. Well done, Marcel. All right, so let's run it through. Call the constructor of child. All right. Call child objects prints. And as I said, we've got two print methods, haven't we? We've got the print in the parent and the print in the child. But we prefer the derived class, the child class, because it's more specific. Okay, it's more specific. The idea, the kind of ground rule, is that the children will extend the parents. So you haven't got the children, you refer to the parents, but if we're calling a function with the same name as the parent, we actually use a special name. We call it overriding. We override the base functionality of the parent and go with a specialist version of print in the child. Okay, so that's what's going on here. All right. Have you heard of overriding before? Yeah, Oscar's nodding. Have you heard of overloading before? No. Okay. Do we know the difference? Maybe we don't know the difference. Maybe I should explain the difference. Okay. Well, you've just seen overriding. You've seen overriding, so we've got two functions with the same name, both called prints, both have exactly the same arguments. Okay. There's no difference between them except for what they do. All right. Same signature, exactly the same signature, but they exist in two different contexts, don't they? We've got one in the child class, one in the parent class. So as we established, the child overrides the parent. Basically ignores what's the parent, overwrites it with the child functionality, all right? If we had overloading, that would be two functions in the same context. So that would be declaring another print in one of these classes, either this class or this class. Let's go with the parent. Let's say we created the nav print here, but we'd have to differentiate it from the other print, wouldn't we? Because again, you get stuck. Which one do we call? How do we know? Which one are we going to refer to? So we'd have to have a sufficiently different signature. You know, we'd have to have a pass in a parameter. We'd have to return something that's different within the signature itself. Obviously, that's easier in other languages because there's a lot more keywords that you can change. I don't think Python actually allows overloading. You can do it in other languages. You can do it in C++, Java, C, etc., but not in Python. But we do have overriding in Python, as you've just seen. Okay, so that's the difference. Overloading would be same class, different signature. Overriding is different classes, same signature. That's a little noteworthy point for you. If you get asked that in an interview situation, have that to hand. Okay, the difference between overloading and overriding in programming terms. Okay, so there we go. Let's move on and let's have a look at another. Oh, here we go. Here's super. I was getting to it, wasn't I? I think this is one of our final sections. So we just said about super. Super refers to the parent, and guess what's happening here? So we're referring to prints, but what do we see? We see two print methods, as we established. Now, we've already established that we're going to prefer the child's print if we're calling it on the child. But what's happening here? Super.print. So what does super refer to?
Parent.
Fantastic, thank you. Which is parents. So we call parents prints here. So let's run this code, and you'll see that it's high from the parent class. So that was exactly what we saw before. We create an object of the child, call the child object's print. So we go to here, okay, call this print, and then we go to super, which is the parent, and call its print. So we go back to here, okay? So this is a way we can actually defer back to the base functionality, the base logic, whatever that is. If we don't want to prefer the child's specialism, whatever that might be, we can go straight back to the parents and say, okay, only use the original function. Don't override it. Don't specialize it in any way. Just refer to the parents. Or potentially we could do both. We could start with the parent's base functionality and then extend it with something unique to the child. So we can actually do a bit of both of what we've just seen there. So there's lots of different configurations. Marcel?
You only have one parent per child.
Yes, correct. You can only have one parent class for a child.
You can have multiple child for.
You can have multiple children, yes. In other languages, in C++, you can have multiple parents, but just be aware that gets complex. It's called multiple inheritance. But in Python, it's only single inheritance, one parent. Multiple children, you have as many children as you want, but one parent for the class.
Can you have a subclass inside of a subclass?
Yes, you can. Grandchildren. So the analogy extends a level down. So you have a grandparent, a parent, and a grandchild. Okay, multiple layers of inheritance. Yes, you can. Yes, it depends how you construct your hierarchy. Depends how you design things. But yes, you can. Yeah. So there we go. There's a way to get back to the parents. All right. So what we could do. Let's finish with this little example. So your students, I'm staff. Let's have a common parent, which is person. We're all people. I'm a person too, thank you. So we're all human beings. So let's have a person class, or call it human if you want. Let's have student, yourselves, which inherit from person. Okay, guess we're putting all the things we've just talked about into action. Got the constructor, got the super, that's the parent, isn't it? So in the parent, what are we doing? We're setting the name for you, students. We'll also do it for me too in just a minute. All right, I've got a name as well. So we're calling the parent's constructor. There it is, init, initialize. There's the Dunder constructor. Okay, pass the name to it, set it there. So we don't have to set it in both the student and in staff. All right. So let's create a student. There we go. Sam's a student. It's got its name. And now let's create a staff class, one for me. I'm also going to inherit from person. I'm going to have a name which is passed to the super, which is the person. Just define it there. Okay, so here we go. Here I am. Staff member Nick. I'm of staff type. We've got a little confirmation here, just if you're wondering. So class staff, class student, 2 classes, 2 children, which inherit from person. Okay. So we could go on to define lots of things that are common between us. In fact, I think this might be leading into our first exercise, so I'll give you a chance to do this. So you might want to then embellish the students, you guys, a class, with all the unique things that you do. You've all got IDs, you're all assigned to modules, library accounts, printing balance, all of that. And I could embellish the staff class with, things that I do as well. So here we go, we're just taking it a bit further, giving you a mark. You can get the mark, okay. Staff, what do? Well, I have objectives. Line managers, they set me things to do. Nick, you've got to do this by the end of the year, they all say, and I've got to go and prove it to them that I've done it. So I have objectives. I suppose you could argue I give you learning objectives, but for the purposes of like management and PDR, I have a named objective, okay, and you guys have got unique attributes. So what we could do is we can blend the 2 things. We can make use of the common functions, the common attributes in super, and we can have unique attributes. Like I said, objectives could be unique to me, and marks could be unique to you. Thankfully, I don't get a mark out of 100 for my objectives. I just get well done. So there we go. That's extended the student and the staff, and let's just wrap up on those 2 things. There's my objective. Nick, you've got to write a blended computer science curriculum. I want it done by the end of the year. So that's what my line managers tell me to do. So that could be my unique objective set there. Reusing the name, which was set in staff. Set in person, I should say, the parent. And this is unique to me, the staff attributes. And then we could do the same for student. So give the student a mark. That resides in the student class, and the name is in the person class. All right, so that's just one example of how we can use a bit of both. Common attributes in the parent, unique attributes in the children, is basically what I'm trying to say here. Okay, so of course we just repeat that pattern. All the things that are unique to you, all the things that are unique to me, and then all the things we share in common. Names, eye colour, hair colour, size, all this stuff, So that's the idea. That's the idea, okay? And I think we'll probably finish on that.